let's finish Module 10 today. Let's talk about concentration. So page 334 plus in your book. The concentration of a chemical is as important as the type of chemical you're working with. The first example they give you is hydrochloric acid. So hydrochloric acid, like in the works, which is a bowl cleaner solution, has 3% concentration of that hydrochloric acid. That means that 97% is water. It's been diluted. There's a very small amount of hydrochloric acid. Most of it is water. Hydrochloric acid here is represented by the pink circles. Muriatic acid, which you can buy in hardware stores, has a concentration of hydrochloric acid of 30%. That means 70% is water. Means it has more hydrochloric acid than the works. It's less diluted. There's less water when you're buying muriatic acid. The amount of hydrochloric acid is higher, 3 versus 30%. And how they react and how they behave is different. The works we can buy and safely put in our toilet and clean our bowl and know that it's not going to dissolve our flesh if it touches our skin. Muriatic acid, on the other hand, is very dangerous and it will burn your skin. So concentration is important when we're doing chemistry. Now, the book also talks about vitamins and toxicity depending on the concentration of that vitamin. So we know that vitamins are good for us, but vitamins can also be dangerous for us. So the right amount of vitamins is okay, but if you take too much of a vitamin, it can kind of poison you. So it gives you examples of that. Vitamin D, if you're taking vitamin D in very high concentrations, more than what it's recommended, is toxic to you and it will give you abdominal cramps, nausea, vomiting, calcium crystal deposits. It will affect the liver, the kidneys, the lungs, and so on. So do you need to know how it affects you? Well, it's interesting to know, but you don't have to know it for any quizzes or for any tests. Just read about it because it's interesting, but you don't have to memorize. Just know that concentration is important when we're talking about chemistry. Okay, there you go. A new concept, the concept of molarity, is abbreviated with a capital M. Later on, you're going to learn about molality. Sounds similar, doesn't it? Molarity versus molality. Molarity is the capital M. Molality is going to be abbreviated with the lowercase m. And they are two different things. So for right now, we're going to concentrate on molarity. What is that? Well, it's a concentration unit that's used in chemistry that will tell you how many moles of a substance are in a liter of a solution. It is determined by taking the number of moles, because you remember that when we have chemical equations, that recipe is in moles. So taking the number of the moles of a substance and dividing by the number of liters of that solution. A lot of times when you buy chemicals, they are solutions. They are being dissolved in water. So it tells you how many moles of that substance is inside that solution. To find molarity, you'll divide the number of moles by the numbers of liters in that solution. And it's very important for you to remember that it's liters of that solution. Now, page 334, so we're moving on. How do we use molarity in chemistry? And they give you an example. We're going to be doing problems, so you're going to get to practice how to do this, but the textbook gives you an example. A 4-liter bottle of muriatic acid, remember that is hydrochloric acid at a concentration of 30%, contains 140 grams of the hydrochloric dissolved. what is the molarity, so the concentration in moles, of the hydrochloric acid in a 4-liter bottle, in 4 liters. To find the molarity, you need to divide the number of moles by the number of liters of that solution. Do we have moles here? No. We have liters, which is great, but they give us grams of hydrochloric acid dissolved. So the first step is going to be, because we don't work with grams or kilograms or any unit of mass, is to translate those grams into moles. And we have learned how to do that. It's been a while since we did it, but you have learned how to do that. I'm going to kind of review here very quickly, but if you forgot how to do this, it's good for you to go back and review it before you move on. You can stop the video and review that. Okay? But here you go. Remember that when you're trying to find the moles given the grams, you need to go to the periodic table and find the atomic mass unit for each atom that is in the molecule. So the hydrogen and the chlorine, and you add them up. So the atomic mass unit total for hydrochloric acid adds up to 36.5 AMUs. And the rule is, if you say, okay, I'm gonna call that grams, then you have 1 mole of that substance. Okay, remember that that is an equivalent. There are experiments that prove that to be true. It's not out of thin air that it came out. We already covered this. But for right now, remember, I'm not calling it AMUs anymore. I'm calling them grams. Now you have 1 mole of that substance. So 1 mole of hydrochloric acid weighs 36.5 grams. Okay, it's been rounded down. Anyway, now we can translate the 1,400 grams of hydrochloric acid to moles. And here it is. You put the grams at the bottom, it's division, 36.5 grams equals 1 mole. So divide this by 36.5 and you'll find out that you have 38 moles of hydrochloric acid. Now, do we have molarity? No. To find the molarity, you need to divide the number of moles that you have by the number of liters. And here you have 4 liters. So you're going to divide 38 by 4 to get a molarity, so the concentration moles per liter of 9.5, capital M, molarity. So the works has a concentration of 0.8 molarity. That's a lot. Okay, so the works is what we use to clean our toilet. So it's a comparison about how powerful this muriatic acid is, and dangerous too. Okay, now we are going to do a problem so you can apply this concept of molarity. Example 10.4 on page 335 reads as follows. What is the concentration in units of molarity of the sodium hydroxide if there are 2.6 moles of the substance in a solution with a volume of 534 milliliters? And then it has a second section. If a student dissolves 124.3 grams of nitric acid in enough water to make 250 milliliters of solution, what is the resulting molarity of that nitric acid? Once we have solved those 2 examples, we're going to do an extra practice problem, number 7 on page 578 in your textbook. Let's move to the board here and let's tackle the first section. So what do they give us? They give us 2.6 moles of sodium hydroxide, and then we have 534 milliliters. That's the information that they give us. And they want to know the molarity. Remember, the molarity equals the number of moles of that substance, so in this case it's sodium hydroxide, divided by the number of liters for the solution. Okay, do we have what we need? Well, we do have the number of moles of the sodium hydroxide, but we don't have liters here. So the first step is going to be convert our milliliters into liters. So 534 milliliters, open the conversion factor and put the units you are trying to get rid of at the bottom, the new units at the top, and write the equivalency. So how many milliliters are in 1 liter? It is 1,000 milliliters in 1 liter. You could also do it the same way the book did it. In the book you have that 0.01 liters is what you have in 1 milliliter. It's the same, okay? It's the same number, the same concept. Whatever works for your brain best, use that. Okay, if you put all the numbers in the calculator, you'll find out that 534 milliliters is the same as 0.534 liters. Do we have everything we need? Yeah, we do. So let's put the information where it belongs. 2.6 moles of sodium hydroxide divided by the liters in this solution, which was 0.534 liters. Do the math and it comes out to 4.9. And what are we calculating? Molarity. So you're going to put a capital M to show molarity. And this is your answer. You're done with these kind of problems. It's not very complicated. The second section here, it says if a student dissolves 124.3 grams and they give you the nitric acid, the formula, and O3, what else did they give you? The water adds up to 250.0 milliliters of that solution. That's the solution. Okay. What is the resulting molarity for that nitric acid? So once again, your molarity, according to the formula, is the number of moles of that nitric acid divided by the number of liters for that solution. Well, do we have that? No. We have grams and we have milliliters. So let's start with, I'm going to start with the solution, just changing the solution, that's the easiest. So milliliters at the bottom, liters at the top, 1,000 milliliters are in a liter. So if I put everything in my calculator, I find out that I have 0.2500 liters. So I have this right here. This is what I calculated, okay? So I have the bottom part, 0.2500 liters. I need to find my moles, okay? To be able to find the moles, I need to know how many grams are in 1 mole for this substance right here. So I need to go to my periodic table. I'm fine. I'm gonna clean this up for a minute, okay? So let me get white for a minute. My molecule looks like this for nitric acid. I need to know the molecular mass of this molecule. How many MUs is this? Start adding them up. I have 1 atom of hydrogen, and if you look at your periodic table, that's 1.01 AMUs. Okay, so all this coming back. The nitrogen is in position 7. I have 1 as well, and each one is 14.0 AMUs. Well, I have, you continue in your page, you have probably enough room to put the next one, but you keep adding. What are you adding now? You should not have put an equal. You're adding the 3 oxygens, so 3 times the oxygen is in position 8 and each one is 16.0 AMUs. Add it up. If you add it up, you find out that the molecule mass is 63.0 AMU. The rule is don't call it AMUs anymore. Call it grams, and then you have 1 mole of that substance. So 1 mole of that nitric acid is 63.0 grams. The problem said that what we had here was 124 grams. So we need to see how many moles are in 124 grams. Let's do that. 124 grams of the nitric acid. I don't want grams of that nitric acid. I want moles. So put always what you're trying to get rid at the bottom. Put the new unit that you want at the top. You remember that. And put the equivalency where it belongs. So 63. Not 6.3. 63. 63.0 grams is 1 mole. Put everything in the calculator and you'll find out that you have actually 1.97 moles of nitric acid in that 124 grams of nitric acid. Now we have everything. So we can calculate molarity. Number of moles of that nitric acid. We just found it. We also found the number of liters for the solution. So put those numbers that you just calculated in the equation. So we have 1.97 moles of the nitric acid divided by 0.2500 liters. If you do the math, you'll find that the molarity is 7.88 m. The units are m. Don't forget your units. Remember that in science, if you don't have units, you don't have anything. So ask questions if this is not making sense. It should make sense. It's not too complicated right now. But if you're having problems, I'm here to help you. Let's do extra practice problem number 7. So let me get my notes. Okay, I have my notes right here. Let me get white. It reads like this, number 7. Give the concentration in molarity, so they want to know molarity, for each of the following solutions. Let's start with A. And remember, molarity is always the same, okay? Number of moles of whatever they're asking, divided by the number of liters for that solution. That is your formula. You're using this formula. So for A, they say that we have 1.11 moles of the hydrochloric acid. It says they are dissolved in enough water to make 1.5 liters of that solution. So basically we do have moles and we have liters. So plug it into the equation. 1.11 moles hydrochloric acid divided by the liters of the solution, 1.5 liters. Put it in your calculator and see what number you get. Let's see, I got 0.74 molarity, and that's the answer for A. Okay. B. For B, it says I have 23.1 grams of the sodium hydroxide dissolved in enough water to make 500 milliliters of that solution. According to the formula, I need moles and I need liters. I don't have moles and I don't have liters, so I'm going to have to convert each one of them first before I can plug them into the formula. So I'm going to try to find how many moles I have in the 23.1 grams. I'm going to do it directly. 23.1 grams of sodium hydroxide. I know that in 1 mole, I'll have the same amount of grams if I add the AMUs for each one of those atoms. Go to the periodic table and find sodium, oxygen, and hydrogen and add them up. So 23.1 16.0 plus 16.0 plus 1.01. I don't call them AMUs, I call it grams. And I put everything in my calculator, and I get like 1 divided by 40 here. So you should get 40 for the amount of grams in 1 mole. And I do the complete math, so everything in the calculator. I get 0.578 moles of that sodium hydroxide. Okay? I'm skipping one step. I'm doing a direct conversion right here. If you like making the extra step and just calculating it separately, do it that way. Whatever works for your brain. But it's the same thing. Add the AMUs for each atom. Call it grams. You have 1 mole of that substance. Do the math, and then you know how many moles are in 23.1 grams. So now I also need, I'm going to erase the top part. And I'm going to go make a line here so you know that I'm still working on this problem, okay? But I need to know how many liters I have here. Well, 500 milliliters. I don't want milliliters, I want liters. I know 1,000 of them are in 1 liter. I do the math, and I know that I have 0.500 liters. Now I have liters and I have moles, so I can plug it into the equation. My molarity is the number of moles, so 0.578 moles of that sodium hydroxide, and the number of liters in the solution, 0.500 liters. Calculate with your calculator, and you'll find that the molarity is 1.16. 16 molarity. Box it so I know where your answer is, and you're done for B. I'm going to erase all of these. Now C. C says that we have 14.5 grams of the carbonic acid in water. How much water? Well, we're making a solution of 200 milliliters of that solution. The molarity requires moles per liter. We have not moles, and we don't have either. We have grams and we have milliliters, so it's exactly like B. We're going to do the same steps. We need to find, so molarity is the number of moles of the acid divided by the number of liters for that solution. And as we don't have any of those things, we need to find them. Let's convert the 14.5 grams of the acid. I'm going to do it directly again, okay? I'm going to open a bracket. I have 2 hydrogens. Each one is 1.01. Then I add 1 for the carbon, and I add 3 for the oxygen, so 16 each. I find the atomic mass units for each one of the atoms. I don't call them AMUs, I call them grams, and I say this is 1 mole of that substance, so that's 1 mole of the acid. I do the math in my calculator, and I find that I have 0.234 moles of the carbonic acid. Okay, so now I do have this number right here, goes right here, okay? So I'm going to put it right here, 0.234 moles of the acid. I'm going to erase this section right here, because this is done. This is a video, so you can go back and study the numbers if you need more. I'm going to put it in red. And now I'm going to find the liters of the solution. I started with 200 milliliters. I don't need milliliters, I need liters. 1,000 milliliters are in 1 liter. I do the math, and I find out I have 0.2000 liters. I put it at the bottom, 0.2000 liters. And I put it all in my calculator. I calculate that my molarity is 1.17 molarity. I box it and I'm done with C. Is there any more? Let me see. Nope, that's the last one for the extra practice problems. Okay, let's see. The dilution equation, page 336. So concentrations can be diluted. What do we mean by diluting? It means just adding water to a solution in order to decrease the concentration. So here we have a concentration, we add water, now that concentration is diluted. The two beakers contain the same number of moles of the solute. If this represents molecules or moles, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, they have the same amount of moles, but one has more water than the other. It's been diluted. The concentration now is diluted. This formula right here is what you need to memorize. This represents the first beaker, this represents the second beaker. If one increases, the other one has to decrease, see, to be the same. So if the molarity, I hope it makes sense, that if one increases, the other one has to decrease for it to be equal. We're going to do a problem, you'll see how this works. But in this formula, the volume does not need to be in liters unless they ask you for liters. It has to be the same unit in both sides for volume. So milliliters and milliliters, or liters and liters, or deciliters and deciliters, it has to be the same unit, but it does not need to be liters unless the problem asks you to give the answer in liters. And you'll see what I mean in a second. Okay? So let's look and see how this works. Page 337, example 10.5. A chemist wants to dilute 12.0 molarity hydrochloric acid to make 500 milliliters of a 3.5 molarity hydrochloric solution. How does he do this? Second section. A chemist takes 2.5 liters of 5.6 molarity sodium hydroxide and dilutes it with enough water to make 10.0 liters. What is the new concentration of the sodium hydroxide? And this is going on all the time in the labs. When you buy a substance that's in a liquid form, it comes in a certain concentration and you may want to dilute it, or maybe you want to take water away by evaporation to make it more concentrated. So you need to know how to do this. And then of course we're going to do extra practice problems 8 and 9 to practice some more, because the more you practice the better you get at this. So let's go to the board here and see how this is done. Let's start with the first section of 10.5, page 337. It says a chemist wants to dilute, and they give you 12.0 molarity of hydrochloric acid to make, okay, it wants to make 500.0 milliliters of what? Of a 3.5 molarity of that hydrochloric solution. Okay? How will he do this? Okay. We're going to be using the formula that I just showed you a minute ago to do that. So basically you have the first beaker and the second beaker. First beaker, second beaker. You have to put it in the right spot to find out. So they want to know basically how to do that. So basically they have given you the volume for the second beaker and the molarity for the second beaker. This is given to you. They give you the molarity for the first beaker, but you don't know how much water basically you're gonna have to add to be able to reach this concentration and have this amount of volume. So they are asking for this volume. Everybody sees that? Let's put it in the equation for a minute. So this represents the first beaker. You start with 12.0 molarity. We don't know the volume here. We have no idea how much volume we need to add to be able to get a 3.5 molarity volume, concentration, and have 500 milliliters of that solution. Okay, so you need to find the volume that you need to add to the original concentration to have a smaller concentration. We do not need to change the milliliters. You can give the volume in milliliters because they did not ask you to give the volume in liters. So rearrange these to find the volume. So anything that's multiplying goes on the other side. This is algebra dividing. I'm going to do that. I'm going to erase this section so I don't have to write it again and put it on the other side dividing. So 12.0 molarity. See that the units work. The molarity here disappears and you're left only with units of volume, which is what you want. Put it all in the calculator and you'll find that your volume, the amount that you need to put in, is 1.5 times 10 to the 2 milliliters. So if you want to create this solution, that's how much water you need to add to the original concentration. Okay, you see, always divide the information into two columns, the original and what you want, and you plug it in where it belongs in the equation. So let's look at number 2, second section here. The chemist takes 2.5 liters of a 5.6 molarity of sodium hydroxide. So I'm going to put 1 and 2 to make sure that you understand that we have like 2 beakers here, kind of thing, like in the picture we saw a minute ago. So originally we have 5.6 molarity of that sodium hydroxide, and it's 2.5 liters that we take from it and dilutes it with enough water to make 10.0. Let me put it in the same space. Let me put it at the bottom so we have all the liters together. 10.0 liters of the new solution. What is the new concentration? So we don't know what the concentration is here. I'm going to leave it like that. That's what you have. But you have the formula that allows you to calculate this. Because molarity 1 times volume 1 does need to equal molarity 2 times volume 2. Let's plug in all the information. Molarity 1 was 5.6 molarity. It's multiplying volume 1, 2.5 liters. Needs to equal. Molarity 2, we don't know. We're trying to find out. But volume 2 is given to you, 10.0 liters. And the units are the same. If they were different, I would have to find a unit, the same unit. We would have to change one of them to have the same units. Now I can find molarity 2. This is an algebra problem. Anything that's multiplying goes on the other side dividing. Because you can divide this by 10.0 liters, and you need to do the same thing at the other side, and then this gets canceled, and you find that molarity, I'm gonna erase this so it looks pretty. Molarity 2, if you do the math, comes up to 1.4 molarity. So this is 1.4 molarity, which is a smaller concentration. It should make sense. You added water. It went from 2.5 liters to 10.02 liters. So the concentration should decrease. Okay, same amount of moles, but now you have increased the amount of the solution. You have increased the solution, so it has more liquid in there. Let's try some extra practice problems. Let's see what I told you a minute ago. So 8 and 9. 8 and 9. Let me get my notes for 8. Let's start with 8. We're doing 8. Says a chemist has a stock solution that is 6.78 molarity hydrochloric acid. That's the stock. That's what came in the bottle. He wants, what does he want? Well, he wants 500 milliliters of a 1.15 molarity of that hydrochloric acid. So what should he do? So basically, you need to calculate volume 1. How much of a liquid, water usually is the liquid, are you gonna add to this concentration to get this concentration and have 500 milliliters of it? So that is M1 times B1 needs to equal M2 times B2. Put everything where it belongs. So you have 6.74 molarity times volume 1, that's the unknown, molarity 1.15 times the volume which is given to you 500. And remember, you don't need to change it to liters. Didn't say give me the information in liters, didn't say that. So divide this by 6.74 molarity, do the same thing on the other side, or just think if it's multiplying on one side, it needs to be on the other side dividing. This is algebra. So this has disappeared from here, and we have the volume isolated, so we can calculate what that volume is. And if you put everything in the calculator, the volume that you need to add comes up to 84.8 milliliters. The moles cancel each other and you were left with milliliters. And number 8 is soft. 9. Let's do 9. 9 reads like this. You need to make, so remember there are always 2 beakers, 1 and 2 beakers, okay? So put the information where it belongs. This helps you. You need to make 0.0 milliliters of a 4.5 molarity solution of potassium chloride, okay? All you can find, so in your lab, what you have is a bottle that has a 5.11 molarity solution. What can you do? Well, you're going to have to add something. You're going to have to add some kind of volume right here to decrease that molarity. You start with 5.11, but you want to end with 4.5. So you have increased the volume. What volume? But let's calculate it. M1 times B1 needs to equal M2 times B2. Put it where it belongs. So 5.11 molarity times a volume we don't know. I'm going to put parentheses, it's easier to see it. Molarity 2 is 4.5 molarity. Multiplying the volume 50.0 milliliters. I can divide by 5.11 molarity. I do the same thing on this side. 5.11 molarity. This has canceled, so it disappears. And I'm left with the volume on one side isolated, and I can put everything in my calculator and calculate this volume. And it comes up to 44 milliliters. So the chemist must take 44 milliliters of this 5.11 molarity solution and add enough water to make 50 milliliters. So it's being diluted. And you need, I didn't say it before on number 8, but you need to explain this, okay? You have to calculate the number, but also tell me what it means. So before, you would have said the chemist must take 84.8 milliliters of the original solution and dilute it with enough water to make 500 milliliters of the new solution. You need to explain what the chemist needs to do, because the question says, what should he do? Okay, so let me write down, for example, the answer for number 9 will be something like this. The chemist must take 44 milliliters of the 5.11 molarity potassium chloride solution and add enough water, so which is diluting, okay, to have the 50.0, this is a 5, I know it's kind of weird, milliliters that he needs, okay? And that's it. You need to put it in writing what the answer is, because they ask you what must he do. And that concludes the extra practice problem. Let's go back to instruction. Okay. Using concentration in stoichiometry. Of course, it's all about stoichiometry, because those are your recipes. You start with original recipes, and you can use them to find out any other information. So from moles, you can go to grams of what you need, but a lot of times, if you don't have a solid reactant, if you have a solution, you're going to need to use concentration. You're going to start with concentration. So concentration molarity allows you to calculate the number of moles, because that's part of the equation. Molarity, capital M, is the number of moles of that solute, of that substance that you're trying to find out, divided by the liters of the solution. So it allows you to calculate moles. And once you have moles, you can do stoichiometry. If you have the number of moles, you can do stoichiometry, period. You don't work with grams. When you're doing equations, you are working with moles, and you need to remember that. But you can translate moles into grams later if you want to, or you can go from grams into moles. You have learned how to do that as well. Now, you can rearrange the molarity equation to find the number of moles. This is at the bottom. It goes on the other side multiplying. And then you have the moles by itself. So moles equals molarity multiplying the liters of the solution. If you don't see this is algebra. Let me work at this for a minute here. I know that some of you are better at algebra than others, but molarity equals the number of moles of your solute. Solute means your substance, divided by the number of liters of the solution. So if you're trying to just have moles by itself, what can you do? You can multiply it by the number of liters of the solution, so you can cancel it. But if you do that, you also need to do it to the other side. That's algebra. So this is canceled, and you're left with the number of moles of whatever substance you're looking for equals the molarity times the number of liters of that solution. Okay? If you want to memorize the new equation, go ahead and memorize the new equation, but just learning the original equation, this right here, allows you to find this equation by using algebra. So let's apply this to a problem, the kind of problems you're going to have to solve this week. Page 340, example 10.6. Says one way to make sodium sulfate is through the reaction of sulfuric acid, and they give you the compound's formula, with sodium hydroxide. How many grams of sodium sulfate can be produced if 500 milliliters of 1.6 molarity sodium hydroxide is reacted with excess of sulfuric acid. And if you remember, excess just means you have too much of it, you're not going to run out of it. Somebody else is the limiting reactant. So let's tackle these one thing at a time. Okay, let me pick up the white here, and the first thing we need to do is find a recipe. We don't have a recipe yet, so we're going to start with the sulfuric acid. I should have put it a little bit closer. That's too far away. Okay, and we are reacting this with what? They say with sodium hydroxide. So that's sodium hydroxide. What are we producing? Well, we're producing, we need to do this ourselves, and we need to balance it ourselves. So I want you to notice that you have an acid and you have a base. This is acid-base chemistry. And you have a base that ends with OH. Meaning what? You're going to create water and a salt. So you know that you're going to create water and you're going to make some kind of salt. So break it apart. Sodium and a hydroxide. Where is this hydroxide going to pick up a hydrogen to make water? Well, from here. I hope everybody sees that. Okay. So what do we have here? We have two hydrogens, and we're left with SO4 2 negative. Everybody sees that? Okay. So basically what I can do is create two waters, but I'm going to need two of these to do that. I need to have two. Maybe I should put it in a different color so you see that this is my thinking process. If I have two hydrogens to create water, I'm going to need another extra hydroxyl. Okay, so that means I'm going to need two of these to be able to do that. Now those two can combine with those two to make two waters. Great. This polyatomic ion can combine with the two sodiums and make the salt. Well, let's do that. So sodium 2, you're using 2, and the polyatomic ion is happy. Is this balanced? It should be balanced. I mean, by just moving atoms around, it should be balanced, but you can count them. You can count each one of the atoms and make sure that it's balanced. I'm telling you it's balanced. But if you don't believe me, you can add them up and see how the number of atoms that came in of each kind is the same number of atoms that came out on the other side. So sodium sulfate, we create sodium sulfate and water. Or salt, which is an ionic compound, and water. Now you have recipe, and we can continue. So that's the first step. What are they saying? It says one way to make sodium sulfate, which we did, was to combine those two, and how many grams of sodium sulfate can be produced. So they want to know the number of grams that you can produce if you start with 500 milliliters at 1.6 molarity of the sodium hydroxide with excess sulfuric acid. It means this one is not going to run out. You don't have to worry about this one. This is the limiting reactant, is the one that decides how much product you're going to produce. That's all they give us. They don't give us anything else. Okay, you remember that in chemistry, this is a recipe in moles. We cannot say, okay, we have grams, and now we have so many grams. No, you have to go to moles. We need to find the number of moles, and then we can translate that into grams. So I need to know how many moles I have here. How many moles is this? So I can do stoichiometry. Once I know the number of moles coming in, I can find out how many moles I'm producing. Well, molarity is the number of moles divided by the number of liters. So from here, I know that the number of moles is the molarity times the number of liters of the solution. Do I have the molarity? Yes, 1.6. Do I have the number of liters? No, I have milliliters. So the first step is going to be converting those milliliters into liters. Let's do that. 500.0 milliliters of this solution. 1,000 milliliters is 1 liter. That means I have 0.500 liters of that solution, okay? Of that solution with the sodium hydroxide. We're talking about sodium hydroxide. You can write it down if you want to. So I'm going to put all the information in here. So molarity, 1.6 molarity, multiplying. I'm going to remember that molarity is just moles per liter. Okay, that's what it is. So you can see how the units come out nicely. So 0.500 liters, the liter will disappear, and you're going to be left with the moles. Okay, that's why the liter could disappear, because molarity is moles per liter, and you need to remember that. So when you do the math, when you put everything in your calculator, you find that you actually have 0.80 moles of that sodium hydroxide. The amount of volume plus the molarity allowed us to calculate the number of moles coming in. So let me erase these and put an arrow that shows that from here we were able to calculate that we have 0.80 moles of that sodium hydroxide. Now that I know the number of moles, I can do stoichiometry. According to my formula, 2 moles are needed to produce 1 mole. You see that? You read 2 to 1. So I can translate 0.80 moles of sodium hydroxide. I open my factor level method. I put the ones that I don't want anymore at the bottom. So the moles of the sodium hydroxide I don't want. I want moles of my sodium sulfate, of the salt. And then I read my recipe and put the moles where they belong. The 2 goes with the sodium hydroxide, so I'm going to put the 2 here, and the 1 is going to go with the sodium sulfate. So I do the math, and I find that I actually was able to produce 0.40 moles of that sodium sulfate. Sodium sulfate. Okay, so I'm going to put it here, 0.40 moles. Okay, because I need to clean up a little bit here to do the last step. Those kind of problems are long, but you need to break them up into steps and reason through. So am I done? No, because they wanted to know the number of grams. But I have a way to find the number of grams. I can find how many grams are in 1 mole of that substance by adding the AMUs for each atom present. I'm going to do it directly. So basically, I would start with 0.40 moles of that sodium sulfate. I know that 1 mole of that sodium sulfate is the same amount of grams as if I add all the AMUs. So go find the sodium in the periodic table. Sodium is in the first column. I'm going to add a bracket here because there are 2 atoms and each one is 23. What else is there? Well, there's a sulfur too. 1 sulfur times, let's see, sulfur, where are you? Sulfur here, number 16 is 32.1. Let me make more room. Put grams here at the back. And add now the oxygens. How many? 4. Each one is 16. So when I add all the AMUs and alkyl I have 1 mole of that substance. And if I do the math, all of these right here adds up to 142.1, which is what is in the book. But I can do it directly. I can put all of these in the calculator with parentheses and brackets and all that stuff and do it directly. But you also can do the extra step and first calculate the 142. So once I do that, I find out that I have actually 57 grams of that sodium sulfate. And that's the answer. That is the answer. That's what they wanted. So step by step, break it down. What do I need? What did they give me? Can I find it? And keep going. If something is missing, go find what you're missing. And you're gonna get there. Just one step at a time. Okay. Now, the last section of the book is experiment 10.2, which is an acid-base titration. You're going to be doing that experiment this week. But I think that we should see some problems, some titration problems before I say, go and do the titration and follow the steps in the book to find out whatever they're asking you in the experiment. I don't want to go over the experiment yet because you have not done it. But I feel like this math is important enough that we should do some problems before you need to do the math in the experiment. So I'm going to cover these right now. What is a titration? I like that name. Page 341, okay? It's a technique to determine the concentration of an acid or a base solution by neutralizing the unknown concentration of a solution, the acid or the base, with the known concentration of the base or the acid. Ooh, this is a mouthful, isn't it? Basically, you know the concentration of one of them, and you're trying to find out the concentration of the other. So if you know the concentration of the acid, you're trying to find the concentration of the base. If you know the concentration of the base, you need to be finding out the concentration of the acid. So it's the opposite. That's all it is. You use one to find the other. So what is neutralizing? Neutralizing means you don't have acid and you don't have base anymore. They've been neutralized. Okay? And it's determined, you know that you have neutralized one by using an indicator. And remember, the indicator is just a substance that will change colors in the presence of an acid or a base. They have two different colors. So it's one color with acid, a different color with a base. So the indicator is one color, and then you drop one more drop and it changes color. Then you stop. You have neutralized whatever you were doing. So if you were adding an acid, you have neutralized the base. If you were using a dropper with a base and your concentration of acid is what you were looking at, then you know the concentration of that acid. Okay? This method allows the quantitative, so you can find numbers, amounts, analysis for the unknown acid or base of the concentration. I know it's a mouthful, but you'll see in a minute. So we're going to do extra practice problem 10 and 11. It's in page 500, both of them are on page 578. It's important for you to understand this problem so you can do experiment 10.2 at home. I'm going to give you this as a PDF, but I'm going to read it to you. If you follow these steps, you'll be able to do these kind of problems. Steps to solve titration problems. Write a balance equation for the reaction given to you. So basically, you always start with writing an equation. If it's not given to you, you need to write the equation and you need to balance it so you can have a recipe. Step 2. Calculate the number of moles for the concentration, so the molarity of the acid or the base given to you. So whatever they gave you, find the molarity of that. And here's the formula. Molarity is the numbers of moles for whatever they give you. If they give you the acid, the acid. If they give you the base, the base. Divided by the number of liters for that solution. At the end point of the titration. So basically, the moment in which the indicator changes color. And you need to remember that you're working with liters here because you're doing molarity. So that's where you can make mistakes. Step 3, calculate the number of moles for the acid or base whose concentration is unknown. And you do this by using stoichiometry. Step 3 means you're going to use the number of moles from step 2 and multiply it by the moles relationship from the balance equation. So you're going to read the equation that you wrote down and balanced because that's your recipe. So that many moles, give me so many moles of the other one. I know this is a mouthful, but we are going to break this down with the examples. Just have this page in front of you and step by step follow the steps and you're going to be fine. The last step is find the concentration as for the acid or the base, whatever concentration we do not have, and you already know how to do that. You have the formulas. So how do we do this? Okay, before we do the problems, this is what you're going to do in experiment 10.2. You know you're done with your titration when it changes color. The indicator changes color. See the color here was blue? You added that last drop and it changed color. You're done. So you have a substance here. You have no idea. You want to know the concentration of that substance. But you do know the concentration and the volume in here. So imagine that this is a base. So here you have an acid. And you have put the acid there. So you know the concentration of this acid and you also know how much volume you had to add until it changed colors. And using those two numbers, you can find the concentration of the base. So here you go. You added the indicator and if you see, it's very fine the line here, but this is kind of a yellowish orangey color, okay? And of course, you're not going to have this equipment. You're going to be using pipettes and beakers, but it's the same concept. So whatever liquid you have here, we decided that this was your acid. You know the concentration of this acid because you created the liquid in here. And then you drop by drop by drop. You keep dropping drops until it changes color. Then you stop. And you read the difference between where you are here and where you started. And this is the volume that you use to do the titration. And those two, the concentration and the volume that you use, will help you find out the concentration of the unknown. In this case was a base. Okay. Let me see for a minute. So 10 and 11, which is what I have here. Let's go to the extra practice problems. Okay, remember to have the PDF handy when you're trying to do these problems, because we're going to do it step by step. So 10 reads like this. A chemist needs to determine the concentration of an unlabeled bottle of bromic acid. So we don't know what the concentration of that acid is. She titrates, means she does this experiment of adding drop by drop by drop until it changes color, the indicator. That's what titration means. She titrates 15.0 milliliters. That's how much volume it dropped in. And it knows the concentration, 1.14 molarity of the sodium hydroxide. So that's the base that you add. It takes 45.0 milliliters of sodium hydroxide to reach the end point. So what is the concentration of that acid? Okay, so I'm gonna draw these so you'll understand what's going on here. We have a bottle here, and inside the bottle we have, in here we have the bromic acid. We don't know the concentration, so molarity unknown, no clue, okay? To find the concentration of an acid, you need a base. If this was a base, you would need an acid, so the opposite. So what acid, base are they using? They're using sodium hydroxide to try to find the molarity here, the concentration of this acid. What are we using? The molarity is 1.14, and she titrates 15 milliliters of it. So here, when we have our beaker and we add the acid to find it, we put 15.0 milliliters. We need the pipette thing, so drop by drop by drop until it changes color. So you added an indicator plus indicator, okay, and you're adding the base. You're adding drop by drop by drop until the indicator changes color. How much of the base did you have to put until it changed color? Well, it says in the problem that you put 45.0 milliliters. When you put that many, then it changes colors, and then you stop. You found the end of the titration. You're done. That's all the information they give us. So how do we find the molarity of this acid? Ready? The first step in your page here says here, balance the chemical equation for the reaction given to you. So we need to do that. We need to create a reaction between this acid and this base. Let me clear these. All these, you should be taking notes. Let's do that. I don't want to make mistakes, so I'm going to get my notes. And have handy the page I gave you, okay? The PDF. First step. So, hide my acid, my base, and remember, you have a base with OH, so you're going to be creating water. And what else? Well, you're going to be creating a salt. So this is Na plus, OH negative, hydrogen is plus, bromide is negative. So these and these make the water, and then these to get together to make the salt. So what do you get? Always put the positive first, the metal, and then the other one. I don't need, oops, I didn't mean to do that. I meant to erase just part of it, so I'm going to write it down again. I don't need to count my atoms to know that it is a balance, because I just broke it down into ions and put them together. So I know this is balance. I'm done. Step 1 done. Step 2, calculate the moles for the concentration or molarity of the acid or base given to you. Well, what did they give to us? They gave us the sodium hydroxide. What did they say? They said that the molarity was 1.14 molarity, and that we use 45.0 milliliters. So, okay, calculate the number of moles from here. The number of moles with the sodium hydroxide equals what? If you remember, it was the molarity times the liters, the number of liters of the solution. Okay? Do we have liters? No, but we can change this into liters. So milliliters into liters, 1,000 of them is 1 liter. So I have 0.045 liters. Now I can put everything in here. 1.14. Molarity is moles per liter, so I can see that I can cancel my liters, times 0.045 liters. So the liters are canceled, and I'm going to be left with moles. How many moles? 0.0513 moles of my base. Okay. So I'm going to copy this number after I erase this, so I have some room. And I'm going to put that number underneath so you can see that we have 0.0513 moles. Okay, we just calculated the moles here. So number 2 is done. Step number 3, calculate the number of moles for the acid or base whose concentration is unknown by doing stoichiometry. So what are we trying to relate? This and this. This is 1 to 1. 1 to 1 means I have the same amount of moles, 0.0513 moles. Okay, so that is done as well. 4 says, find the concentration asked. So they're asking for the concentration here. They want to know the molarity. This is what we need to find out. How do we do that? Well, the molarity is going to be the number of moles of the acid that we don't know divided by the number of liters in that solution. Remember that we had 15. I think that's what the problem said. Let me look at it again, but I think that's what it said. Going back to read it. Yeah, they give us 15.0 milliliters. Well, I do have the number of moles, but I don't have liters of the solution because I had milliliters. So I need to change that. Milliliters to liters. 1,000 to 1. So if I do that, I find out that I have 0.0150 liters. And now I have everything I need. Number of moles, 0.0513 moles divided by the 0.0150 liters. And if I do that, I can find out that my concentration for that bottle that was unknown is 3.42 molarity, moles per liter. And that concludes that kind of a problem. Okay? So let's do 11. Let's do 11. So your experiment is going to be this kind of math. You're going to be doing this at the same time as you're doing the experiment. You're going to try to find out a concentration that is unknown. So 11 says, I'm going to just start drawing. We have our bottle here, probably of an unknown. This is our bottle with the top and everything, okay? It says 50.0 milliliters of an unknown concentration of, so here we have a molarity we don't know. And this bottle is of magnesium hydroxide. So now we have a base here that we don't know. And it says in our beaker, when we start with our beaker, I'm already going to do that. In our beaker, we have 50.0 milliliters of this magnesium hydroxide. Remember that in your experiment, you add indicator. And then you start your titration. This is a pipette, by the way. Not very pretty, but you start adding drops. Of what are you drying? Well, if you have a base, you're going to have to add an acid. That's what titration is. And you are titrating with hydrochloric acid, it says here, with a known concentration of 1.00 molarity. The end point, so means when the indicator changes color, is reached when you have used 3.51 milliliters of this acid. So with all this information, you are able to find the concentration of this base right here. Follow the steps in the PDF I provided. First step says, write a balanced chemical equation between the two, the acid and the base. Let's do that. So we have hydrochloric acid plus my magnesium hydroxide. Break apart what you have here. You have two of them and a magnesium. What do you have here? Potassium, so the potassium, the hydrogen, and the chlorine. Well, remember that when you have a hydroxyl base, you're going to create water. So you're going to be creating some kind of water, we don't know how much, plus a salt. I have two hydroxyl groups. Each one can create one water, but I don't have enough hydrogen here to do that. So I need two of these molecules. And if I do that, then I'll have enough hydrogens to make everybody happy. This and this will combine with this and this, and we'll make two waters. Now I have two chlorine or chloride ions and a magnesium ion. The charges work out perfectly. So my salt, so with the magnesium, because that's my positive, my metal, and then add how many chlorines I'm using. I'm using 2. And I don't need to count atoms. I know it's balanced because I just did the chemistry one atom at a time. So this is balanced. I'm done with balancing the equation. I'm done with step number 1. For step number 2, now I need to calculate the number of moles for the concentration of what is given to me. Well, what did they give to me? If you remember, they give us the concentration of the hydrochloric acid. And what did they say? Well, they said that we had 1.00 molarity of this acid, and we ended with 3.51 milliliters used before the indicator changed colors. When we ended, we had used 3.51 milliliters. Okay, from here I can find the number of moles. Well, what's the number of moles? Equals the molarity times the number of liters in here. We're talking about hydrochloric acid. Do I have a molarity? Yes. Do I have number of liters? No. Let's change it. 1,000 is 1 liter. So do the math. And let's see. I know I have 0.00351 liters of the hydrochloric acid. Now I do have everything I need. 1.00 molarity multiplying the 0.00351 liters, and I'm going to end with moles. When I do that, I find that I have the 0.00351 moles of hydrochloric acid. Okay, so I found number 2. I'm going to erase this part and just put the number we found underneath it. So I just found that this is 0.00351 moles. Okay, so we have the moles. Step 3, do stoichiometry. So what are we trying to find? We're trying to find the moles of our base. I need to put them together, 2 to 1. I don't have to. I start with 0.00351 moles of hydrochloric acid. I don't want moles of hydrochloric acid. I want moles of my base, magnesium hydroxide. And I read it. The 2 goes with the hydrochloric acid. I put it to here. The 1 goes with my base, and I do the math. When I do the math, I find out that I actually have 0.00176 moles of the base. Okay, I'm going to put it right here to keep it tidy so I can make room. I'm going to erase this section right here because we just did that. And we're done with number 3. Step 4. Find the concentration asked. Well, new color. Molarity of the magnesium hydroxide is what? The number of moles of the magnesium hydroxide divided by the number of liters for that magnesium hydroxide solution. They did give us the amount of the solution. We had 50 milliliters. And the first thing we need to notice is that we don't have liters. So we need to change that. Milliliters to liters, 1,000 to 1. So when I do the math, I find that I have 0.0500 liters in that solution. Now I can find out my molarity. So the moles we found out, 0.00176 moles. We translated the milliliters to the liters, so we have the right units. We put that number down. We put everything in the calculator, and I find out that my molarity for this base is 0.0352 molarity. And this is the answer, okay? That's the molarity of the bottle that we didn't know. And we found out by experimentation. The experimentation is called titration, drop by drop by drop, finding the volume, finding the moles, doing stoichiometry, and basically going back to the molarity. So if you follow the steps, you're going to be fine. Ask questions. When we have our Zoom meeting, ask questions. We'll talk about the results of the experiment before you turn them in. Let me see. This is the experiment you're going to be doing, and this concludes Module 10. You're done with Module 10. We're almost done for the year. So read your textbook, add to your notes if you need to, review examples if you need to, ask questions, work on your own and correct them as you do the problems, because you don't want to make the same mistake over and over. Study for the quiz, do the labs, review questions, and practice problems. And that concludes Module 10. See you soon. Bye-bye.